Avery, thank you so much for being here.
My pleasure.
We're so excited to talk to you. Personally, I think that black holes are the most fascinating, amazing things in the universe, and you're my favorite person to explain black holes. You're the source of all of my knowledge of black holes. So I'm hoping you can tell us the news that has come out about black holes and the Event Horizon Telescope that you're involved with. What's new? What's happening with black holes?
First, Colin, let me say you're my favorite person in the universe now too, because you love the same thing I love. I shouldn't say that because, of course, my favorite people are the family that support us and make this all possible. You're my favorite PR person.
I'll take it.
Favorite podcaster.
All right.
So, sorry, Lauren.
Tied for first.
Tied for
favorite
yes,
podcast.
Yes.
Got it.
Well, she can be my favorite in a minute. Depends on how she starts her question.
All right.
The news now is the Event Horizon Telescope has now released the image of the second black hole that it has observed. And this black hole is the one at the center of our very own galaxy, right? So this is near and dear to us. And it looks very much like the first image that we released 3 years ago. It's a fire donut on the sky, okay? But it's an important and I think striking confirmation that the first image was not unique, it was not special, we didn't get lucky, that in fact, imaging the event horizons of black holes is a going concern. We now have done it with 2 objects, and it looks the way that Einstein and many others afterwards predicted.
And you mentioned the first one a few years ago. Can you tell us about that one? And you said they look similar, but they also have differences, significant differences in size.
Absolutely, yeah. So what we released 3 years ago was an image of the 6.5 billion solar mass. So it's not just the mass of the sun, which dwarfs, of course, the mass of any terrestrial object, but of the sun and 6.5 billion of its closest friends, almost the mass of a galaxy, all collected into one point in space out in the giant elliptical galaxy Messier 87, 54 million light years away, right? So it's an enormous distance away. From the photons that left M87, departed the black hole, the dinosaurs had just gone extinct. Mammals had not yet become ascendant, right? It's an incredible distance, mind-boggling scales. The one that we just saw today, the one that we just released today, it came from the same observation run, but it's the black hole at the center of our galaxy. Okay, so it's still a long distance away. If you wanted to get into your car and drive there, it would take you about as long, essentially an infinite amount of time. I don't know what gas mileage your car gets, but it's I guess unless you're Elon Musk.
If your car went the speed of light, just to clarify, you could get there in how many million years?
24,000.
24,000. That's
24,000 years. So that means that the light that left Sag A star, that's the name we give the black hole at the center of our galaxy, left in the late Stone Age, right? So not only were there humans, but they were well on their way to becoming what we are now. So it really drives home how much closer this new beast is. But it's closer, but it's also 1,000 times, 1,500 times less massive. It's a very different object, very much more typical, not this really extreme kind of thing that M87 was. It's our black hole, so I think a lot of us feel an affinity for it. And it means that it changes, right? So M87 is the stately old lion, just sitting there, letting us take its photograph every night. Sag A star is the puppy that's constantly moving around, wagging its tail, won't stay still, and on minutes, maybe hours time scales, presents a completely different face. And that's a massive difference, right? Different time scale that it takes to image it, different time scale that things are changing on.
So how do you do this? How do we image black holes?
Well, so with great difficulty and with a global group of extraordinary people who all come together for this one purpose, right? So the imaging of M87, the imaging of Sag A star, begins with telescopes at the far reaches, far corners of the Earth, each planning and executing coordinated observing campaigns, collecting these subtle photons from the universe, recording them on literally tons of hard drives. That then gets shipped back to a central facility where we try to piece together what is effectively an Earth-sized telescope. So then once we have these little bits of information pieced together in an Earth-sized telescope, then we can complete the process of forming an image in a large supercomputer. And that involves effectively implementing something like an inverse Fourier transform, unmixing the little bits of information from each of these around the globe.
So with some difficulty then.
A little bit, yes. Yeah.
And it's a really involved procedure, but at the end of the day, you're getting this one image that we can look at. As you said, it looks like a fire donut. What are we seeing when we look at that image?
Right, yeah, so the fire in the fire donut is the luminous hot plasma that has rushed headlong towards its inexorable fate, crossing the event horizon out of the visible universe, right? So, black holes are a nice place to look, but if you linger too long, you're in trouble. And that plasma is lingering too long. But by virtue of having fallen down deep into the potential well presented by the black hole, it has heated up to enormous temperatures, billions of degrees, hundreds of billions of degrees. And that's producing the fire that we see. That's what we would call synchrotron emission. It's an emission mechanism that happens when you have very energetic electrons, very hot electrons zipping around magnetic fields. But the hole in the donut, which is, of course, the defining feature, that's the black hole. That's the gravitational bending of light around the central black hole, leaves behind a shadow. And that's the defining feature. We talk about the Event Horizon Telescope. That's what we were built to observe.
Shadow.
I always thought black holes were, by definition, impossible to see, impossible to photograph. And the idea that there's the icing around the donut, in my initial perception would be, well, everything falls in and you can't see anything. So what are we seeing light that has just barely escaped from this pit of gravity?
Right. Yeah. So the darkness of black holes, that's an isolated black hole statement, right? Black holes are definitely the perfect prison. Nothing escapes, even light. But black holes plus the stuff, that's the icing, right? That they are the most luminous objects in the universe. What we're seeing is emitted far enough out that it's not quite so dire, right? So a non-trivial fraction of the light is captured and absorbed by the black hole. Depending on where exactly we're talking about, it can be as high as 50%, maybe less. So I don't know. What kind of odds do you want to give our photon?
Not great.
Not great. Yeah. So yeah, it's an extreme environment, but it's not right up against the horizon.
Right.
And yeah, I want to go back to this word horizon because you've said it a few times and it's even in the name of the Event Horizon Telescope. What's the event horizon and where is that on the image?
The event horizon is mathematically that point of no return, right? It is the surface in space that separates those things that can reach out to infinity and those things that can't, right? So a good definition might be the event horizon is that line you cross when people stop responding to your tweets, right? that puts it in a very contemporary frame. In the image, the reason why we see a dark shadow is because light can't traverse through the black hole itself, right? The light that tries to traverse through the black hole would cross that event horizon. And then that's captured forevermore, and that's what leaves this deficit that you can see from any vantage point, right? So it's kind of a funny idea that no matter what direction you're looking at the black hole at, it casts the same shadow on the surrounding material, and it's because the light can't propagate through this event horizon and come back to us. So that shadow we see is literally the image of the event horizon, or the absence of image from the event horizon.
Right.
I remember one of the first times I ever spoke to you, this was about 8 years ago, you said, we're working on getting the first image of a black hole, and mark my words, when we do, It'll be on the front page of the New York Times above the fold. And then you announced it, and the next day, I remember I picked you up at the airport, and I looked at the newsstand, and there's there's the black hole on the front page of the New York Times above the fold. And I thought, well, he got that prediction correct, and the predictions of the black hole itself were correct. But why do you think there's such a public fascination? It's the New York Times above the fold is prime real estate for an object that's impossibly far away for us to ever experience.
Oh, absolutely. This is one of the great joys of working on black holes. I think it connects with people on a deep level. I think most people they may not have a mathematically exact concept of what a black hole is, but black holes have penetrated the public consciousness so well that most people have a reasonable conceptual idea, right? There's that perfect prison from which nothing escapes. Maybe they see them in movies. Black holes don't suck, okay, but beyond that, they're not Hoovers sucking up the universe. But the idea of a thing that you go into and you don't come out, it also ends up being a useful reference for many things that people experience, right? I mean, there's a real mystery. What happens on the other side of that event horizon, and how would you know? Mm-hmm. You can't send an undergraduate across the event horizon and then report back to you, right? They cross the event horizon, and it's a mystery, right? And that's an obvious metaphor.
There's also ethical reasons why you shouldn't send an undergraduate to the black hole.
Undoubtedly, yes. And practical. It's very, very expensive. You would at least send a graduate student. But it's it's a metaphor for changes in life that you can't see the other side of, right? So people, on a visceral sense, connect with it, and it's visual, right? So, a large part of your brain is focused on visual processing. So this is an important, profound science result that talks about these kind of extreme objects that people already kind of get, and it's presented to them in a format that they can easily absorb, right? So I think that's why this ends up being a really exciting prospect for public engagement.
And as you said, it relies on a global collaboration. Can you talk a little bit about that collaboration? How many people, where the different telescopes are located?
And maybe your role in that collaboration. Which piece of the puzzle are you?
Right. Yeah, so the collaboration is more than 400 people. They are on 6 of the 7 continents. We managed to get onto Antarctica before Australia. We haven't. There's not enough tall mountains in Australia. We'll have to find a solution for that. These are people who range from engineers who design and build hardware, put steel on the ground, all the way to people like me, theorists who try to make sense of what we see. Right. So my role in all of this has been trying to determine, what does it mean that we see this particular brand of fire donut? Is it a French crawler? Is it a Boston cream? And what does that mean for black holes and how they impact the galaxy? The telescopes are at the highest, driest sites on Earth. That's absolutely critical because we are looking at millimeter wavelength photons. These are about 10 times smaller than the size of photons that are bouncing around your microwaves, right? And we the reason why you use, well, a few times smaller than your microwaves. The reason why we use microwave ovens is because those photons are absorbed well by water. So that's if you put a steak in the microwave and it comes out feeling and looking like you boiled a steak, that's because that's what you did. You heated up all the water and you cooked the steak with the hot water inside the steak. So that's slightly tragic because we have these photons that came from the late Stone Age, from the center of our galaxy, or just after the end of the dinosaurs from M87. They've traversed the universe to come to us, and in that last moment of their journey, they slam into our upper atmosphere and get absorbed by water. Right? I mean, it's sort of a brutal Game of Thrones type.
That
Game
long
of Thrones
journey, and then just shy of reaching us, they
no payoff.
Oh man.
And so we try to help those photons by getting above as much of the water as we can. So you have to be in those highest locations and try to choose the places that don't have lots of water. So the South Pole is a good example. First, it's pretty high. And second, the water has precipitated out. It's all frozen out. Chile, the Atacama Plain, almost built on a high plateau that's in the middle of a desert. Mauna Kea in Hawaii is a mountain that protrudes up very high, and it's in a very stable thermal environment because of the Pacific Ocean. And so all of these places, high and dry, help us get to these photons before the water vapor does.
And the EHT has been described by you and others as an Earth-sized telescope. Can you explain what you mean by that?
Yeah. So all astronomical observations must fundamentally contend with the wave nature of light. And it's unfortunately not an option, right? Light's a wave, and that means that when we see small structures, they get blurred out by something called diffraction. You experience diffraction, and as I get older, I might see it a little worse than I did before, but you experience diffraction every time you drive at night and you look out into the distance and you see the street lights. You'll notice they all look like little stars, not stars in the sky, but multi-pointed
Starbursts.
Starbursts. Yes, thank you. And if you look closely, you'll notice that every street light looks like the same star.
Mm-hmm.
And if you turn your head, the star moves with your head. It's always oriented the same way. And that's because the star is not in the light, it's in your eye. You're looking at diffraction spikes through your pupil. You see this in movies when you see the diffraction spikes from the camera. You can tell how many sides their pupil on the camera has, or how many sides they thought the pupil on the camera would have when they do it all in post-processing and add lens flare and things.
Right, the J.J. Abrams shot.
That's right.
Got
right. And so the same thing happens in astronomical instruments, and your ability to resolve something goes down as your telescope gets bigger. As I should put that. Let me turn that around. The smallest thing you resolve gets smaller as your telescope gets bigger. Bigger telescope, you can see smaller objects. At millimeter wavelengths, which is where, right, microwaves that the EHT observes, we really do need a telescope that is the size of the planet Earth, right? The 10,000 kilometer diameter telescope. That's an unpopular thing to build in people's backyards. They somehow object if you completely cover their entire yard in shade. The solution, though, is that it turns out you don't need the whole telescope. You just need to fill in enough of it to spread out across that 10,000 kilometers. And the Event Horizon Telescope uses this very clever technique where we have telescopes that are spaced around the world, and they're each filling in fact, it's each pair of them are filling in a little point on this mirror. And so then the strategy is, one, more telescopes is better because we get more points on the mirror. And two, patience, because the Earth rotates underneath the sky. And as the Earth rotates, those telescopes are at different locations and they're filling in a different part of the mirror. And so when we say we have an Earth-sized telescope, we mean that very literally, right? So we really do effectively construct a sparsely sampled, but nevertheless Earth-sized primary mirror. It's also a computational telescope because that process has to be completed in large computers after the fact, which is effectively propagating the photons from the mirror, where normally you would have the mirror, you reflect your photons off the mirror up to your primary focus, and then you'd make your image there. We reflect we detect the photons on the mirror, and then on a computer say, well, this photon would have done this up to our primary focus, and then we make images.
So all of these telescopes that existed for other purposes, they were built for other astronomical uses, you've sort of hijacked isn't the right word, piggybacked, capitalized.
Borrowed.
What's the good word? Borrowed. made the most of.
Leverage.
There's the word I was looking
Leverage,
for.
yes.
So these telescopes weren't built themselves for black hole hunting. Is that right?
That's right.
Okay.
That's right. In fact, one of the largest telescopes in the world, if not the largest, this Atacama Large Millimeter Array. It's this telescope in the Chilean desert. Canada is a partner. It's so big that it couldn't be made with a single region, right? So it's got Europe, it's got North America, and it's got the Asian partners. And they all came together and they built this one enormous radio telescope. $2 billion. And this was not the thing they built it for. They built it for a whole host of things, finding birthplaces of planets, protoplanetary disks, or the disks around young stars where planets form. One of the first images it produced shows these beautiful rings where you can see the planets are forming inside of the gas and dust disk around a young star. Understanding what stars, how stars form, understanding the formation and evolution of galaxies, and any number of other things. I'm shortchanging ALMA by a long shot. Then there's a whole bunch of other telescopes that were built for very similar purposes, none of which by themselves could even hope to do the experiment that we're doing. And so what the Event Horizon Telescope really did was provide the secret sauce, or the clever application that connects them all, right? And it's a good example of how you can have a lot of excellent pieces, but until you assemble them, maybe there's something you're missing, right? The EHT is really allows these telescopes together to be far more than the sum of their parts.
How did you even conceive, you or your colleagues think of, maybe if we connect these telescopes, we can resolve this mysterious object? Where did this idea come from to build the EHT?
So to be fair, this technique, radio interferometry, is a venerable technique. So I mentioned ALMA. I went on and on about ALMA a moment ago. It actually uses radio interferometry. It's 64 individual dishes that all connect up to form one effective telescope that's maybe 10 kilometers across, 100 kilometers across sometimes. They move the dishes around. The idea of using telescopes separated by Earth-sized distances also is not new. People have been doing that for almost half a century. There's the very long baseline array. So the technique is very long baseline interferometry, and there is a dedicated array that does this very long baseline array at much longer wavelengths. Okay, so 7 millimeters is really pushing it, and then they go all the way out to meter wavelength. So the VLBA has been doing this for 30 years. What's new in the EHT is pushing that technique down to 1 millimeter. Right? There's a sweet spot. It is expensive to make the Earth bigger. Right? You can do it at the price of launching rockets. Right? But it's difficult otherwise to make the Earth bigger. But if you want to improve the resolution, the other thing you can do is observe at shorter and shorter wavelengths, higher and higher frequencies, bluer and bluer color. And the Event Horizon Telescope really is the clever element of figuring out how to make that technique, which is very challenging, provides very significant tolerances at each station, work on this heterogeneous array of telescopes that were otherwise already built to do the millimeter science, in part for the reasons why I talked about microwaves. It's because looking at water is interesting. It's not just water that shows up in the microwave range.
And these are features of the technique in general. Did you have to modify or improve any of the techniques when you went from studying M87 to studying Sag A star?
So the observational side of it is the same. In fact, it's the same observing rod. Right. So the detecting those subtle radio photons, that was effectively identical. But because Sag A star is that frenetic puppy and constantly changing, that means that if we are patient, as we have to be to make an image, because we do have to fill in that mirror, right? Remember, that mirror is just a couple points. I mean, you can imagine what it would be like trying to get ready in the morning, and all you have are 15 points on your mirror, maybe 15 little dime-sized pieces. Some of us might be able to do that, but most of us won't. The patience part fills that in, is absolutely critical. And that's the part that is a real problem for Sagittarius Star, because as we are patient, Sagittarius Star's changing, right? So it's really like we're leaving the shutter open, trying to get that photo in dim light, and the puppy is not standing still. In fact, we're chasing it around. And so that required a whole new, already the M87 required a whole new set of tools to operate in a challenging data environment. The Event Horizon Telescope, as wonderful as it is still just barely capable of doing what we ask. I mean, it's really a groundbreaking instrument, which also means that you're the first to find all the difficulties, all the problems. We don't have enough telescopes. We always want more telescope. We don't have enough pieces of that mirror. We always want more. There are some calibration challenges that we hadn't anticipated that we had to overcome. We had to rewrite most of the data processing software. I mean, there are packages that people use for the VLBA for these other instruments, and they just did not work for EHT. But then on top of that, we had to relax this patience assumption. We could just stare at it, leave the shutter open, and make a picture. And that required, I think, a revolution in how we think about making these sorts of pictures. We had to develop that's what took us the 3 years. We had to develop the analysis techniques necessary to allow us to be patient.
And so as you're saying, these results, these images that you come up with, they take years of effort from many different people. And how do you choose which black hole you're going to focus on? What factors do you consider?
Yeah, unfortunately, that's easy.
Sounds like the one easy thing
that's
so far.
Yeah. You observe the black holes you have, not the black holes you wish you had, right? As this groundbreaking experiment, and being confined to Earthsized baselines, Earthsized mirrors, we really only have two choices. There's only two black holes that exhibit a shadow that we could resolve, that we are aware of. And those are the black holes in M87 and the black hole at the center of our galaxy. The one at the center of our galaxy, because it's so close, it's very typical in many ways, but it's right next door. And the one in M87, because it's just so enormous. It's much further, but it's also much larger. And those two, that's it. And then after that, the next one is 3 times smaller. So just barely on the cusp. Of course, we do look at other objects. There's a lot of interesting science to be done, to be looking at mostly accreting black holes. But those are the only two what we call horizon science targets, targets where we can resolve the fire donut, resolve the shadow.
And I have to ask you about the fire donut, why you're calling it a fire donut.
Yeah. Well, that was one of the members of the EHT, just before the first announcement, put our M87 picture into a Google image search, just to find out what Google thought this might look like. And so I think actually there were some predictions that came up. That's not the fun ones, though. The fun one is they came up with fire, rings of fire, and donuts, and hence also because it's a little bit fuzzy. I know we have this picture of very sharp ring-like structures from these beautiful numerical simulations that run on supercomputers. But we're just pushing the envelope. We're just at the boundary. The resolution we have is what we show, and that kind of smears it out into this. Looks kind of like a French roller.
You said to us the other day, though, that these two black holes that you have now are kind of like an odd couple. And if you had to choose just two, there are two pretty good black holes to have at your disposal now. Can you explain why that is?
There's the movers and shakers in the universe, and then there's everybody else, right? And black holes are the engines of the universe, pumping out huge amounts of energy, but that's only a subset. M87 is one of these very powerful, certainly historically powerful black holes. It sits at an enormous galaxy in an enormous galaxy cluster. There's thousands of galaxies all orbiting each other, right? So it's not just that it sits in a galaxy that's 100 times more massive than our own, but it's also in a cluster of thousands of galaxies. And it's down at the center of all of that, benefiting from all that commotion driving gas down to it. And while these days it's on something of a starvation diet, certainly historically it wasn't. That's how it got to be 6.5 billion times the mass of the sun. And it powers a powerful outflow. It powers what we call a jet. These are light speed emanation, right? Remember, black hole's perfect prison, right? This is exactly the opposite of what you would expect. Stuff going out, not in. And that stuff is being launched right near the event horizon. And we think we understand something about how that works. But this one of the goals of the EHT is really to nail that down. So that's M87, launching these kind of counterintuitive, paradoxical light speed outflows, center of all the commotion, center of all things. The one at the center of our galaxy is the black hole next door. It's really this typical average black hole. Our galaxy is kind of the typical average galaxy. It's ours, so we like it, but it's not terribly unique. And at a 4 million solar masses, our black hole is really similar to all the other ones. We only see it because we're so close to it.
Right.
It's on a starvation diet, and were it a couple galaxies away, we would not be able to see it.
Right.
Right. So it is as different as you could imagine one of these enormous behemoths, these supermassive monsters, the centers of galaxies could be. We have one powering a jet. It's enormous in the center of the all the commotion. And then we have another one that's kind of typical of everything else, not really growing very much, not feasting on very much gas, hardly observable, almost shy. And it is the comparison then that allows you to ask questions like, why? Why is our black hole little and that one big? I'm not complaining, right? I don't want to live next to M87, right? That would probably be dangerous. But why? What makes a black hole produce those light speed outflows? What allows a black hole to grow very fast? What determines how bright they are, how big they are?
And you've said, these are your words, there's a monster, a supermassive fire donut behaving like an unruly puppy in our neighborhood. Should we be scared? This all sounds very scary.
Yeah, right. Well, it's the astronomical neighborhood, right?
Right.
So
not right next door.
Not right next door. That's 24,000 light years is a comfortable distance for now. We're not about to be. Remember, black holes don't suck. It's a great line for a 6th grade class. The black hole at the center of our galaxy, even at 4 million times the mass of the sun, is only massive enough to rule the gravity in its area, rule the dynamics of material in its area, for a distance that's kind of typical of the distance between stars where we are. Okay, so it has almost no more authority than the sun, right? The sun is ruling the area around in our vicinity about that distance as well. Now, there's a lot more stuff there, so it's a little bit more impressive. It has a larger retinue of more interesting things, but nevertheless, it's relatively small because the mass of the galaxy is 10 billion times that of the sun, right? So at 4 million with an M instead of 10 billion with a B, it's still a tiny fraction of the galaxy, which is part of the magic trick. How do black holes achieve such enormous energy output while being such a tiny fraction of the mass of their host galaxy? So it's not gonna suck us up. We're not gonna fall into it, at least not in any time scale that is even astronomically conceivable. We will long before that. The sun will have grown into a supergiant, enveloped the Earth, gone out.
Oh, great!
Yeah. I mean, like there's other things. I'm not saying don't be worried. I'm just saying that's not. But that doesn't mean that it's safe.
Mm-hmm.
And that's because if it ever decides to go off the starvation diet, it can suddenly start producing a lot of high energy emission, a lot of X-rays, a lot of ultraviolet, a lot of gamma rays. And we know that 1,000,000 years ago it was doing that. There are these giant bubbles of hot stuff above and below the plane of the Milky Way galaxy. And it's believed that that is caused by a episode of energetic behavior, an episode of rapid accretion, which suddenly produced a lot of energy, produced jets like we see in M87, those light speed outflows.
But we haven't seen in Sag A star.
Not any evidence in the past 1,000,000 years.
Mm-hmm.
In fact, everything you see looks like the luminosity is dropping exponentially, dropping like a rock. So now's the time to do this, right?
Mm-hmm.
1,000,000 years from now, it might not be. If it ever did that again, who knows? We might all get irradiated. But living next to an active galactic nucleus is a little dangerous.
You did say, you gave us an analogy the other day of it's like living in the plane next to a cosmic volcano. It's dormant,
Yeah.
but it may not always stay dormant.
Exactly. That's right. It might be beautiful at night as long as it's not erupting.
And you make these nice analogies to the type of diet that the black hole is on, whether it's starving or feasting. Does this affect how difficult it is to measure it?
Yes. I mean, there's a sweet spot between starved and feasting that we have to hit, right? So absolutely. If it's feasting, it's bright, and that sounds good. It's easier to see bright objects. I mean, these things are so dim. Astronomers have a special unit because it just gets really cumbersome to carry around 10 to the minus 26 all the time. It doesn't matter what unit you're talking about. If it's 10 to the minus 26 something. So it's 10 to the minus 26 watts per second per hertz. Okay, so compare that to we all used to have 100-watt light bulb, right? Now we all have 15-watt light bulb, right? The LEDs, but 10 to the minus 26 watt. Okay, that's what astronomers are measuring. It's really incredible. And that's a bright source. We call that a Jansky. A Jansky source is a pretty bright source. Sagittarius stars 3 Janskys, 2.5 Jansky. And if it were rapidly accreting, that'd be brighter. It's easier to see. On the other hand, at some point, what we mean by rapid accretion is that gas is rushing headlong down towards the black hole, and more accretion means more gas. You put too much gas, it becomes opaque. Then you can't see the shadow. And then we're just, the big bright ball at the center of the galaxy telescope. That's not that fun. So Event Horizon Telescope, we have a sweet spot. It has to be accreting enough. It has to be feasting enough that it's bright. And there are some galaxies that aren't. M31, the Andromeda galaxy, right? So you can see that in the night sky. That's the black hole at the center of that one is a little too dim. And then on the flip side, it can't be feasting too much. It has to be starving a little bit, or else we won't be able to see through the material around it to get that horizon.
Is there a spot on the night sky where we could go out and look and say Sagittarius A star is roughly there, in the Sagittarius constellation?
In fact, yeah. That's why it's Sagittarius A star. That's right. So the center of our galaxy is located in the constellation Sagittarius. It's a teapot. From the northern hemisphere, you're really right on the limb.
Mm-hmm.
I've never been able, actually, in my backyard to see it because the light pollution and trees, and so it's always been a sore spot for me. At some point, I'm going to get into the southern hemisphere, and the only time that I was in the southern hemisphere, I was in Australia. They had brush fires, so you couldn't see anything.
Yeah,
I was really bummed. And I'm a theorist, so I didn't even know I was the wrong. I asked some of my observing colleagues, okay, so where would I have looked? And then they kind of looked up at the sky and they thought for a second. They said, well, at around noon, look at the sun. So I was also the wrong time of year, so I was going to help. But
sounds like bad advice.
Yeah.
At high noon, stare at the sun.
Yeah, exactly. I guess that's why we don't have any in the EHT. But it's in the constellation Sagittarius, right? And this is where the name comes from, right? It's the brightest radio source in Sagittarius. We call it Sagittarius A. and it's a point source, which means until now it wasn't resolvable as a structure. It was just a single spot of light, so that became star.
And does this black hole in the center of our galaxy, does it affect the shape or the structure or the motion or anything of the galaxy surrounding it?
No, only the dynamics of the stars right around it. Right? So
Mhm.
these are the stars that Andrea Ghez and Reinhard Genzel won a Nobel Prize in 2020 for watching for decades. And they watched them orbit the black hole,
Mhm.
and from that measure its mass. It's only those stars really that are being dramatically affected. But this is a deep question because we do know that big galaxies, I mean, M87 is a big galaxy, has a big black hole. Small galaxies have smaller black holes. And, why is that? It's certainly a correlation that people observe. It doesn't sound that unreasonable that, whatever allows a big galaxy to accumulate all the gas and all the mass that produces all the stars that you see in it, also will accumulate stuff at the center, which forms a black hole. That might make sense. On the other hand, we know that's not the whole story because we do know that black holes like M87 are producing those light speed outflows. They can outshine their galaxies by factors of 100. And they're producing prodigious amounts of energy. It's mind-boggling. And that energy is not just coming out as light. It's not just coming out as radio waves. It's also coming out as kinetic energy in outflows. It's pushing material out. It's a giant
Actual
snowplow.
stuff, matter.
That's right, actual matter, and you can watch that process happen. So by this what we call feedback, gas falls down into the center of the galaxy. It feeds the black hole, which then enters this very active state, starts pushing all this stuff around. It's kind of like an unruly baby. It's throwing everything against the wall. You can limit how fast more gas can rain into the galaxy, rain into the galactic halo. And so that black hole, even though it can only affect the dynamics of the things right around its environment, can spread that influence out to the size of the galaxy, out to beyond the size of the galaxy, the size of clusters. The largest examples of these jets that we see extend many times the distance from the galaxy. This is an intergalactic impact, all from that point, that most compact thing you can think of, down deep at the center.
Amazing.
And you've said a few times that you're a theorist, and so while this collaboration requires people with a lot of different expertise, you focus on theoretical analysis. Can you tell us a little bit about the specific questions or topics that you focus on studying?
Yeah, so 20 years ago, I started thinking about trying to explain the phenomenology of some of these objects, some of these accreting black holes, and understand what it is that resulted in the distribution of light that we see, the polarimetric properties that we see, the variability properties that we see, and that was inextricably tied up with what's happening down at the event horizon. So how these black holes grow, how they launch those outflows. And that led me right away to be trying to make models of what that plasma, that astrophysical fluff around the black hole that is so important for the astronomers, for us, making numerical prediction, explicit predictions for what that looked like. And then I did a thing which is dangerous for a theorist, as I thought, maybe we can answer this question on timescales that matter for my career. Right? I have a kind of a rule of thumb I try to follow. I try to make predictions that can be proven or disproven in about 10 years. I think my going time scale is about 15 years. So that's pretty good for an astrophysicist. It's within a factor of 2, so I'm satisfied.
Considering you're looking at light that started in this direction when the dinosaurs were around.
How did M87 know?
Yeah.
Right. No, that's right. So it's so originally I'm building these models, trying to ascertain what is the right observation that's going to allow me to distinguish between different ways black holes can grow and different ways they can launch outflows and how that affects their otherwise observed properties, and how that how that relates to how gravity works, right? I mean, black holes, we've talked about them as very astronomical objects, but they're also, this kind of perfect mix of traits for general relativity. Extremely simple solutions to Einstein's equations on the one hand, and yet completely counterintuitive physics, extreme physics in every other sense. It's all nonlinear gravity. So it's a natural place to go look for any test, any deviation from general relativity. I think you'll. My uncle once asked me, Avery, if you found that general relativity was not right, would you report that? And I had to explain to him that we're all theorists, we're all raging egomaniacs. The one thing we want to do is knock Einstein off the pedestal so we can climb onto it. Right? That's what we're all hoping to find: some inkling, some hint, which we may already have seen, that there's something not kosher in the theory of general relativity, something not quite right that we have to fix up. We have theoretical reasons for thinking that has to be the case, but observationally, it's been quite difficult. And the place you might look, the natural place to look, would be right around black holes. But since that time, I've really gotten into actually trying to make those tests work, right? And so this is where I come into the Event Horizon Telescope. My job is not to come up with the ideas that motivate the telescope. We did that, right? We're working on ideas for the next telescope, but we did that. And now we're working on trying to test them and trying to bring those theoretical concepts into direct contact with the underlying observation. So what prediction do we make for the fire donuts, right? And so for M87, one of them was it should be bright in the south, not bright in the west. And that was a little weird. That sounds like a very boring prediction, but the reason is because that light speed emanation goes west. It's about 10 degrees north of west. It just goes west. And so you would have thought that if there was a bright side to the black hole, it's in the direction of the emanation. But no, it's not, because that material is rotating very rapidly. And we see the side that's coming towards us. It's a searchlight effect. When I say rapid, it's rotating at half the speed of light. There's a searchlight effect, and the mission gets beamed in the direction that it's moving. So we see it, the side that's coming towards us, and that's the south. So that the jet as a whole, it's all spiraling around the jet, is going towards the east. And that's not true further out in the jet, because the jet gets wider, and it's just angular momentum conservation. It's just the figure skater expanding her arms, slowing down. But at the black hole, the arms are all tucked in, nice and tight, and we see it bright in the south. So that's the kind of prediction that we made. For Sag A*, we have predictions about how much it can vary. So how frenetic is the puppy, right? It's not enough to say frenetic puppy. We want to know, did this puppy just wake up? Is he tired? Has he received a little bit of training? Is it a high-strung puppy? Is it a chill puppy? It's like these are, we have a quantification of all of that. And it turns out that the large-scale numerical simulations that we have that give us a purchase on that question are a little bit too variable. So there's a mystery, right? We don't really know. It's like, are those really applicable? Was there an ingredient we just missed? Did we forget to put the baking soda in or something? The cookies are flat. And we'll find out, right? This leaves something exciting to think about and try to develop going forward. But building out those direct tests, direct contact with the data is where we've been focused for the past 5 years.
I'm curious about the Sagittarius A star, the black hole in our Milky Way. How did it come to be there? How was it formed? Why is there a black hole there?
That was a brilliant question. I don't know. So there's two kinds of black holes that we observe in the universe, right? So we have the things like we've been talking about. We call supermassive because they're very, very massive. We think every galaxy has one at its heart. Sometimes you'll see two. And we think that's because the galaxies, we do see galaxies run into each other, merging galaxies. They'll ultimately settle down and combine and distribute. And when that happens, the two will merge and become one. Mm-hmm. But one of these big ones per galaxy. The other kind of black hole that we see in the universe, that doesn't mean there aren't other ones. these are the two that we have direct evidence for, are what we call stellar mass black holes, which is also inconveniently SMBH, right? So supermassive black holes, stellar mass black holes. And the stellar mass black holes are the end products of every star over about 30 solar masses, right? So a star that grows beyond 30 solar masses during its formation, has a unique sentence, right? There's nothing it's going to do that's going to stop it from forming one of these stellar mass black holes at the end. Now we know that these very, very massive stars live only a very short time, right? So they live only about 1 million years, many 100,000 years. So when you generate a massive star, as far as astronomers are concerned, the universe is concerned, in the blink of an eye, you've now made a stellar mass black hole. One of these things that's 10, maybe 30 times the mass of the sun. There's some heavy ones,
which we haven't seen direct.
We haven't imaged them, but LIGO, right? So this is a gravitational wave experiment where they're looking not at light, not at the subtle ripples in the electromagnetic fields that we pick up, but subtle ripples in the gravitational field. A subtle jiggling due to ripples in space-time. They are seeing the merger of these stellar mass black holes. So we know they're there. We do see them.
The famous LIGO discovery was two black holes eventually slamming into one another.
That's right.
Right.
Exactly. So LIGO's, very inefficient. Every time they find two, they lose one. EHT is, very, very environmentally friendly, right? We see one black hole at a time and we leave it be. But it's a very exciting, dynamical event. Unfortunately, I can't give you a formation story. You asked, where do these supermassive black holes come from? I can't give you the formation story for the ones at the center of galaxies. I know that if I have to wait for one of these stars to form, right? I mean, stars don't just automatically form in the universe out of nothing, right? The first stars are very different from the stars you see right now. The stars you see right now have all kinds of heavy elements in them that were created in the furnace of earlier stars. The first stars don't have that, right? The first stars are made out of just what the universe had at the beginning. So they look very different. The James Webb Space Telescope, one of the things that it's designed to do is go see those and tell us about them. If you wait for those to form and then create a stellar mass black hole and then start growing, you put them in a very advantageous place. You let them gobble up all the gas they can get their hands on. And there's a limit to how much they can get their hands on. First, you can only grab what you can gravitationally access. And second, if you start trying to eat too much, it gets in the way. When you eat too much, at some point you start shining too brightly, and the light that you're putting out, the electromagnetic radiation you put out, starts pushing back on the flow. It becomes self-regulating, right? Just look at a hot dog eating contest, right? At some point you can't go any faster. And that fundamentally limits how fast they can grow. And if you put in that limit, we call that the Eddington limit, after Sir Arthur Eddington, who first identified it. If you say they're growing at the Eddington limit at that maximum rate, they can't get to the sizes that we see some quasars at in the universe, right? So we know there are these supermassive black holes floating around earlier than you could make from a stellar mass black hole. So now, how do you do it? I don't know. It's a great question.
Is that part of what the EHT is hoping to figure out, how these things come to be?
Well, so if there was a way to circumvent Sir Arthur Eddington's limit, that would be one way. And so studying that, not just looking at the gravity, but not the essential gravity, some sense the gravitational stage on which all of the astrophysical dramas play out, but instead looking at those astrophysical dramas, we try to determine, how does accretion onto black holes work? Is it really subject to the assumptions that go into the Eddington limit? Could you exceed it by orders of magnitude? And if you can, then we can solve that problem. The other thing is of course, there's a future beyond the EHT. And there's a near future But then there's a far future, which is the one. I get excited about both. They're both wonderful, but the one I dream about is the far future, of course, of EHT in space.
Mm-hmm.
We've made the Earth 100 times bigger by virtue of putting satellites out there with radio dishes. This is something that you could actually talk about doing. This is a project that's accessible, these technologically, just about accessible today. So this is something we could be thinking about 30 years, 50 years from now. Timeline's always very long for that. And if you built an instrument like that, we could see every M87 in the universe, right? So that would have the resolution necessary to see M87 all the way to the edge of the universe, which is a remarkable thing. Now, they're not all bright enough to see, okay? But that means that you're really talking about looking at black holes and their evolution across cosmic time. And this gets to exactly this question. How did they grow? How did they get to be so big?
Is M87 one of the biggest we know of? Are there other M87s floating around, or is it an anomaly?
There are other similarly sized objects in the universe, but they are anomalies. So I think the 10 billion solar masses is about the limit. There's a category of ultramassive black holes, which are defined as bigger than 10 billion, right? So, I mean, we're getting into the superlative game, right? So,
this is where the mind reels, because these numbers are just impossible for me to comprehend. I think impossible for most people. How do you wrap your head around these distances and sizes and scales?
Don't. They're numbers.
You shut up and
you just write them down. It's a really great question. How do you internalize or connect these things to a terrestrial scale? And it really is not. I think it's not possible. You could compare. You say, well, M87 is bigger than Sagittarius star, so you get and similar things, right? How many 10 billion? How many 1 billion? You do that kind of game, right? But what does it mean to be a 10 billion solar mass? I don't know. It's simply enormous.
And to add another number to this, do theorists have estimates for how many black holes there are in the whole universe?
Well, one per galaxy, right? So if I put my Carl Sagan hat on, that's billions upon billions, right? In our galaxy, remember I said before that every 30 solar mass black hole makes a 30 mass a solar mass star makes a black hole. And there's a certain number of 30 solar mass stars you make for every solar mass star, for every star like the sun. And stars like the sun don't die in a million years, right? They last 10 billion years. Okay, so every solar type star in the galaxy about is still sticking around, right? Maybe some have gone, but it's still of the young with it generation. Every half solar mass star in the universe still exists, right? They have not run out of fuel yet. So you can just look at the number of solar mass stars, the number of half solar mass stars, and you can estimate how many 30 solar mass stars must there have been. And remember, they fly by in the blink of an eye, right? It's 10,000 times brighter, 10,000 times shorter lives. The candle that burns 10,000 times as bright burns 10,000 times shorter lives, right? As long, 10,000ths. Okay. So these are short-lived, so they're almost instantly transferred. So we can estimate how many of these stellar mass black holes there are in the Milky Way, and the answer is millions. And so we talked earlier, is Sagittarius star going to get us? No, but I've started calling the closest black hole. We don't know what it is, right? It is the closest known black hole. You'll hear about that every now and then in the news. The closest black hole, called Proxima opie, closest hole. It's probably something like 20, 30 light years away, right? I mean, you could send a mission to it if you knew where to send it.
Right.
Again, people think about going to nearest stars. You see all these science fiction movies going to the nearest habitable planet. Well, maybe it will stop at the nearest black hole on the way. You just have to figure out where it is. And this comes back to black holes being so difficult to see. Hardly know where they were, and so we have something that's right next to us. We have no idea where it is.
Amazing. Avery, you have a very cool job, and I'm curious, how did you get into this? How did you get into black hole research?
Um, well, I first, like many people, I love science fiction, love Star Trek. Just watch original Star Trek all the time. And the thing that I loved about Star Trek, aside from the kind of sciencey stuff and the phasers, and of course now we all have communicators and the like. They stopped flipping a while ago, but anyway, it, one of the things that I really liked about it was the exploration. The idea that they would every episode go someplace new, see something never seen before, right? And so that motivated me, being scientifically or mathematically inclined, to seek out a job where I get to travel the universe. And Starfleet didn't exist, so I couldn't go on a starship. But I guess you could go now. Right? Musk is making Starship.
Can you afford it?
Can you afford it? No, it's getting cheaper every day. So there was no Starfleet to join to go investigate or explore the universe. So instead, I found a job where I could explore the universe on computers and on blackboards and in my mind. And that's what astronomy really is, right? It's a way to go and see the most extreme, most unusual environments in the universe and try to understand them, right? So after becoming enamored with that, my path is pretty similar. Went to university, majored in math and physics, and couldn't get enough, and so never left.
And does it feel like you're getting to do that? You're getting to explore the universe with this research and others?
Absolutely. I couldn't have done it any better than able to put images of black holes up on view screen.
Mm-hmm.
It's basically an episode right out of Star Trek.
Do you know what you want to explore next?
Well, that's a great question. We have had our heads down the grinding wheel for so long. We don't think much about what to look for next. But really, this era of resolving event horizons has just begun, and we are now in a special period where it's not just the Event Horizon Telescope, but we also have LIGO. We also have neutrino experiments that are looking at the universe not in terms of electromagnetic waves or gravitational waves, but neutrinos as particles. We have the CTA, the Cherenkov Telescope Array, looking at the universe in high energy gamma rays. Again, a very different way to look at it. And all of these are focused predominantly on black hole. And so we are at the era where the theoretical musings of Schwarzschild and Kerr and Einstein, when they thought about the things that nobody could ever possibly see, that's being seen. Black hole science has gone from being theoretical to being empirical over the past 10 years, 5 years. And we're just at the beginning. And so, the things that occupy my future time, in as much as I find it, are really thinking about how to move from making that first image to doing something akin to black hole meteorology. Right? I don't want to see a picture. I want to see beautiful high resolution movies. I want to see magnetic flux tubes, little magnetic vortices zipping around. I want to see flares popping off, look like solar flares or solar coronal mass ejection, sudden snapping of magnetic field lines and huge amounts of energy going off right around the event horizon, tracking all of these things in real time, and then understanding how that all interplays with the gravity of black holes. Right? So I think the future in this context is higher resolution, higher cadence, higher sensitivity. it's our Olympics of black hole science. Was it stronger, faster, higher? So yeah, that's my future, right? And there's ways to do that. We talk about the next generation EHT, the NGHT. This is not an evolution of the Event Horizon Telescope, but a revolution of the Event Horizon Telescope, where we add 10 or more new dishes that are dedicated to doing this sort of millimeter VLBI, this sort of
On top of the
Earth-sized
existing
telescope,
telescopes already part
on
of it?
top of the existing
Wow.
ones, right? And every telescope you add is not just one piece better, because it's really the number of pairs of telescopes, right? The way we fill in that mirror goes as the square of the number of telescopes. So the difference between 20 and 8 is not the difference. It's not 12, right? It's 400 versus 64. It's a massive difference. And so that's going to allow us to start mapping out that black hole meteorology to very large distances away from the black hole. So how do you connect the environment to the horizon? And then there's that space kind of, fantasy almost, right? Musings about EHT in space, which we have to start doing now if it's going to happen. And that just opens up, the entire universe to this sort of thing. Now we're not talking about 2, maybe 10 targets if we really push it. We're talking about million, right? So that would be an extraordinary change, right? So then we would go from theoretical black hole science to empirical black hole science to surveys, right?
Mm-hmm.
Having so much data, who knows what you're going to do with all of it, what you're going to find.
And I'm curious, when you look at these images that you get, I remember in 2019 with the M87 image, when you sort of had the image, you came up to me and said, "Colin, you want to see something?" And you showed me on your phone. I was like, "That's incredible! I'm one of the first people on Earth to see this image." But you were probably among the very, very first. And with the Sag A star too, you've now been among the first people on Earth to see something. What's that like for you? And are you able to look at that data and the fire donut and sort of let your imagination take you to the place itself?
Well, so often those first imaging experiments, you're just trying to get everything to work right. So there's a sense of elation, which doesn't necessarily come from the importance of the moment, but oh, thank God it finally did what I asked. We actually produced some of the first images of Sagittarius A at a workshop right here at Perimeter, and shortly after M87 in August 2019. We had a workshop to identify the main challenges and began game planning out how we were going to solve all of them. And it turned out that many of those, I think all of those game plans are what we ended up following. So that was a momentous meeting. And there we did see, we didn't share. So we kind of sequester the groups. Each analysis team is trying to make their particular image with their particular method, and we have a method that we use. But everybody was producing images, and you kind of knew that we were getting something good because everyone was smiling a lot. We produced the first image, and it looks about like what we thought it should look like. There was a lot of happiness in that room. Did we feel the weight of history, thinking, "Oh, we've seen this thing for the first time"? I'm not sure I'd go that far.
That was
But
just
we
me.
do now. We do look back on it, and we think, it's a very special thing, right? M87 was seen by half the human beings on planet Earth, and we're talking about Sag A star today. It was just released, but I imagine that it will also be seen by a similar number. And there's few cultural phenomena that transcend at that level. It's an amazing privilege to be part of that.
Well, Avery, thank you so much for spending this time with us and once again helping us understand black holes and the EHT. It's like I said, it's one of my favorite subjects. Thank you.
Well, my pleasure. And thank you for having me, Lauren and Colin.